Okay, so today we are doing lecture 8.4, and that has to do with multiplying, subtracting, and adding radical expressions. So in order to do that, let's get into adding and subtracting first. And in order to add or subtract radical expressions, we use the distributive property. And that is something that you probably forgot about, but we are going to refamiliarize ourselves with that. So first of all, definition, like radicals, are radicals with the same index and radicand. So same index means that we have to be taking the same root. So like both need to be square roots, or both needs to be cube roots, or both needs to be fourth roots, that sort of thing. And same radicand means that the thing underneath the root needs to be the same number. So like, for example, our first problem has the square root of 11, and that matches in 4 square root of 11 plus 8 square root of 11. So those are the same, so we can go ahead and add as indicated. And in order to do that, we use the distributive property, and that works in the following way. So if we have 4 square root of 11 plus 8 square root of 11, we can think of that as 4 plus 8 square root of 11. And we know that 4 plus 8 is equal to 12. So our final answer would be 12 square root of 11. So in order to add like radicals, first of all, needs to means that the radical expressions need to be exactly the same. So in this case, our square root of 11s exactly are the same and they match. And it also means that we kind of treat it almost like a variable. We're not adding 11 and 11 and getting square root of 22. We're not doing anything weird. We kind of just leave that square root of 11 as is, and then think of the addition almost separately to that, okay? So the answer to number 1 would be 12 square root of 11. Let's do number 2. Number 2, we have 5 times the cube root of 5x minus 7 times the cube root of 3x. And again, we think of, okay, first we need to check that our roots are the same. I have the cube root of 5x here, and I have the cube root of 3x here. And now that I'm looking at that, those are actually supposed to be the same. So that is supposed to be 3x, because otherwise this example wouldn't work. And I want this example to work. So this is going to be 5 times the cube root of 3x minus 7 times the cube root of 3x. And so now we check, do our radicals match? The answer is yes. Check, check. And so now we can think about this as 5 minus 7 times the cube root of 3x. We know that 5 minus 7 is equal to -2, and then we have that cube root of 3x. So our final answer for number 2 would be -2 times the cube root of 3x. And then number 3, we have 2 square root of 7 plus 2 cube root of 7. And this one is not a typo. I wanted to put an example there that where our indexes didn't actually match, and so you couldn't do anything. So we can't actually do anything with this problem. The above problem that had a typo in it, you could not have done anything with, but I wanted that one to match, and so we could actually do that subtraction. But this one was meant to be like this. Our indexes do not match, right? We have a square root here, and we have a cube root here. And so since those are not the same, we cannot do anything. And our final answer would just be equals 2 square root of 7 plus 2 times cube root of 7. There's no simplification or addition or subtraction that we can do there. All right, so we're going to move on to some more examples of this, because there are a lot of different ways that we might see these types of problems. So next up, we have the square root of 20 plus 2 times the square root of 45. So we know that square root of 20 and square root of 45 do not have perfect square roots. And so we want to simplify the square root of 20 and the square root of 45 such that we can maybe perform more addition in this case. So let's start with square root of 20. The largest perfect square that multiplies into there would be 4. So I'm going to break up 20 into 4 times 5, which is square root of 4 times square root of 5, which is equal to 2 square root of 5. So I'm going to rewrite 20 as 2 square root of 5. And then we have square root of 45. I want to try and break up my square root of 45. If I think about 45, the largest perfect square that divides into 45, I accidentally wrote a 9 because the largest perfect square is 9. So I'm going to rewrite 45 as square root of 9 times 5, which is square root of 9 times square root of 5, which is equal to 3 square root of 5. So I have plus 2 times 3 square root of 5. And then I have 2 square root of 5 plus 2 times 3 is equal to 6 square root of 5. 2 plus 6 is equal to 8. And so my final answer is going to be 8 square root of 5. So it turns out that I was actually able to simplify square root of 20 and square root of 45 such that I had a like radical that I was then able to add. Let's do another example. Next up, we have cube root of 54 minus 5 times the cube root of 16 plus the cube root of 2. So let's start with the cube root of 54. The cube root of 54, I can simplify to the cube root of 27 times 2. So cube root of 27 times the cube root of 2. I know that the cube root of 27 is 3, so I can rewrite this as 3 times the cube root of 2. 3 times the cube root of 2. Then we want to look at the cube root of 16. The largest perfect cube that divides into 16 is going to be 8. So I can rewrite this as the cube root of 8 times 2, which is equal to cube root of 8 times the cube root of 2. Cube root of 8 is 2, so I'm going to have 2 times the cube root of 2. So minus 5 times the cube root of 16 was simplified to 2 cube root of 2 plus the cube root of 2. There's no way I can simplify that last piece anymore. So then I have 3 times the cube root of 2 minus 5 times 2 is 10 times the cube root of 2 plus the cube root of 2. And I can actually think about that as 1 cube root of 2 because there is that 1 outside there that is implied. So then I can think of this as 3 minus 10 plus 1 times cube root of 2. And I know that 3 minus 10 plus 1 is going to give me negative 6 cube root of 2. So my final answer for number 2 there would be negative 6 times the cube root of 2. And then last example we have is the cube root of 48y to the 4th plus the cube root of 6y to the 4th. So again, I want to break up these radicals so I get perfect cubes. So the cube root of 48y to the 4th. So first I'm going to think about this in terms of numbers. The largest perfect cube that divides into 48 is going to be 8, I believe. So that's going to be the cube root of 8 times 6. And then remember, when my exponent in a variable expression is a multiple of my index, then it will have a perfect root. So y to the 4th, I'm going to break up into y cubed times y to the 1, because I know that y cubed will have a perfect cube root. So then I have the cube root of 8 times the cube root of 6 times the cube root of y cubed times the cube root of y. The cube root of 8 is 2. The cube root of 6 does not simplify. The cube root of y cubed is y, and the cube root of y does not simplify. So I could rewrite this as 2y times the cubed root of 6y. So I know that 48, the cube root of 48y to the 4th is actually 2y times the cube root of 6y. And then I have plus the cube root of 6y to the 4th. So I'm going to want to go ahead and simplify the cube root of 6y to the 4th. So let's go ahead and look at that. The cube root of 6y to the 4th. I'm going to want to break that y to the 4th into something that has a perfect cube, which will be y squared. So I'm going to have the cube root of 6y cubed times y, which could be broken up into the cube root of 6 times the cube root of y cubed times the cube root of y. The cube root of 6 doesn't simplify, so the cube root of 6 stays. The cube root of y cubed is y, and then the cube root of y does not simplify. So this would be equal to y times the cube root of 6y. So I have 2y plus y times the cube root of 6y. And then since I now have like radicals, the cube root of 6y, I can think about this as 2y plus y times the cube root of 6y. 2y plus y is equal to 3y. So my final answer would be 3y times the cube root of 6y. So that one is tricky because it has a lot of moving pieces, but as long as you keep track of what you know and remember that you're just breaking up radicals like we already know how to do, then you will be fine on these problems. All right, let's do a couple more examples with fractions. So we have the square root of 45 over 4 minus the square root of 5 over 3. And so to subtract, we want to know that the least common denominator is going to be 12. And so you want to identify an LCD. But first, actually, let's simplify our radicals. So square root of 45, my largest perfect square is 9. So I know that square root of 45 simplifies to 3 square root of 5. So this is the same thing as 3 square root of 5 over 4 minus square root of 5 over 3. Except for I cannot simplify I cannot do subtraction of fractions when the denominator is not the same, no matter what's in my numerator. So I know that in order to make this over 12, I need to multiply by 3, and to make this over 12, I need to multiply by 4. So I have 3 times 3 square root of 5 over 12 minus 4 square root of 5 over 12. 3 times 3 is 9, so my numerator up here is going to be 9 square root of 5. And then I can think about that as equal. So 9 square root of 5 minus 4 square root of 5 over 12. And then again, since I have like radicals, I can think about this as 9 minus 4 square root of 5 over 12. We know that 9 minus 4 is equal to 5, so this is going to be 5 square root of 5 over 12. So don't let those fractions trip you up. It's literally the exact same process that we know and are comfortable with. And then next up, we have the cube root of 7x over 8 plus 2 times the cube root of 7x. Okay, so let's go ahead and apply our quotient rule for radicals. So we know this is going to be the cube root of 7x over the cube root of 8 plus 2 times the cube root of 7x. And then we want to go ahead and simplify. We know that the cube root of 8 is in fact 2. So I'm going to rewrite my denominator here as 2. And then I want to go ahead and make sure that I have a common denominator so I can do my addition. And that common denominator is going to be 1. So I need to multiply my second. The common denominator is 2. Sorry. So I need to multiply my second expression by 2. So I will have the cube root of 7x over 2. That guy doesn't change. Plus 2 times 2 cube root of 7x over 2. 2 times 2 is equal to 4. So I'm going to go ahead and rewrite that as 4. So I have the cube root of 7x plus 4 times the cube root of 7x. So I can think about that as 1 times the cube root of x. So that then I can think about this problem, since I now have like radicals, as 1 plus 4 cube root of 7x over 2. 1 plus 4 equals 5. So I'm going to have 5 times the cube root of 7x over 2 as my final answer there. So again, don't let the fractions trip you up. You know how to do things with fractions, you know how to add and subtract, and you need that LCD. Now, part 2 is multiplying radical expressions, and we multiply radical expressions in the same way that we might multiply polynomial expressions. So basically distributing. So let's look at some examples. Number one, we have the square root of 3. The square root of 3 times 5 plus the square root of 30. Let's go ahead and simplify, or actually what you can do then is, so we're going to think about distributing that square root of 3. So I'm going to have square root of 3 times 5 plus square root of 3 times square root of 30. Right here, I can use my product rule for radicals and rewrite this as 5 square root of 3 times the square root of 30 times 3, which is equal to 30, 60, 90. Then I want to go ahead and simplify that square root of 90. So square root of 90 is equal to the largest perfect square that divides evenly into it. So that's going to be square root of 9 times 10. So square root of 9 times square root of 10. So that's going to be 3 square root of 10. So I'm going to have 5 square root of 3 plus 3 square root of 10. And then there is nothing I can actually do with that because they are not like radicals. So my final answer would be 5 root 3 plus 3 root 10. Next up, I have square root of 5 minus square root of 6 times square root of 7 plus 1. And the way that we multiply out this expression is actually using FOIL, just as if these were binomials. So I want my first, so I want square root of 5 times square root of 7 plus outside, so square root of 5 times 1 inside minus square root of 6 times square root of 7, and last minus square root of 6 times 1. And then I can go ahead and do a little bit of simplification here. So 5 times 7 is 35. So I'm going to get square root of 35 plus square root of 5 minus 6 times 7 is 42. So square root of 42 minus 6 times 1 is 6 square root of 6. So my final answer would be root 35 plus root 5 minus root 42 minus root 6. Nothing actually really combines there. And that's our final answer. And then last but not least, we have 4 square root of 3 minus 1 quantity squared. So we are going to actually rewrite that as 4 square root of 3 minus 1 times 4 square root of 3 minus 1. And we can see we have a binomial times a binomial, which we want to now FOIL out. So 4 square root of 3 times 4 square root of 3 is first outside minus 1 times 4 square root of 3, inside minus 1 times 4 square root of 3, last minus negative 1 times negative 1, which would just be plus 1. So then I know that I have 4 square root of 3 times 4 square root of 3, which is going to be 16 times the square root of 3 squared. If I have the square root of 3 times the square root of 3, squaring something undoes my square root. So I'm just going to have equals 3. So I'm going to have 16 times 3 minus 4 square root of 3 minus 4 square root of 3 plus 1. 16 times 3 is equal to 48. So I'm going to have 48 minus, I have 4 square root of 3 here and 4 square root of 3 here. Those are like radicals, so I can go ahead and write that as minus 4, negative 4 minus 8 square root of 3 plus 1. 48 plus 1 is 49, so I'm going to have 49 minus 8 square root of 3. So take a second with this problem or actually all 3 of these problems with multiplication, and make sure you take a second to look at all the steps, see if you're following along with them, see if they make sense to you. And if they do not, then go ahead and ask questions in class. Hopefully the practice problems on Math Lab help you kind of understand this a little better, but if not, please come see me. I'm more than happy to help you out. So thank you for watching. Have a great day, guys.